All right, so let's take a look at an example of the steady state diffusion problem in this module. And so this is going to be, again, a quiz question. So I'll have you listen to the instructions and then pause the video, try to work it out yourself, answer the quiz question, and then come back and we will work this one together. Okay, so this question, much like the example we talked about in the previous module, is again a steady state diffusion problem. But in this case, we're looking at membranes or materials that protect meat in the store, right? So that plastic film that comes on your meat packages when you buy it at the store. So the idea of this is obviously you want to keep out bugs and whatnot, but also keeping out oxygen makes the meat look better and keeps it from aging or rotting as fast, right? So we want to keep out oxygen. And so in this example, our meat is protected by a plastic film that's 1 millimeter thick. And we want to look at the flux of oxygen across that membrane so that we can determine if it's going to affect the product, the meat. So we're given the diffusion coefficient. Make sure you're kind of keeping track on the units and making sure everything cancels out. And then we're also given the surface concentrations, right? So this is the mass concentration of oxygen on the exterior, basically in your supermarket, and then C2 would be the oxygen concentration inside the package. So set up the problem just like we did in the previous module and see if you can determine the flux of oxygen across that membrane. So do that, pause the video, come back, and we will discuss. All right, so hopefully you've had a chance to look at that, and let's look over the solution and see if you got the same thing. All right, so I've drawn it out here for you. Sorry about my dogs. So we've got the oxygen side, the supermarket, right, and then the inside the meat package, and then our plastic wrap here in blue, and we want to basically solve that steady state diffusion problem. And so the first thing is we're going to assume a linear concentration gradient. So we know the concentrations on either side, and we know the thickness, and we're going to assume it goes linear through that, and so we can set up the slope of that. We also know D from the problem statement, and so if we're going to plug that in, the concentrations in D, and then our X value at the bottom, the x2 minus x1 is the thickness. So it gives us the thickness as 1 millimeter or 0.1 centimeters. So we switched it to centimeters so that the units all match up. And so at that point, you'll get basically 0.97 or close to 1, and that's 10 to the minus 13 grams per centimeter squared second. Again, it may be hard to kind of visualize or think of what this number means without comparison. But as you can imagine, 10 to the minus 13 is a pretty small mass for that. And so this is a pretty small amount of oxygen that makes it through a given area per second. And so that's a good thing, right? But if you wanted to compare different plastic films, right, this number would help you determine which one would be best for eliminating the oxygen. And so if the concentrations, so the other part about this is if you're picking a material, right, the thickness isn't going to change unless you purposely change it. And the concentrations we can assume are the same. And so really it comes down to this diffusion coefficient. And that's the predominant factor if you're looking at a comparison between multiple materials. So that's something to keep in mind too. The other ways that you could think about it would be increasing the thickness and what effect that has, and then obviously increasing the concentrations or adjusting that and seeing how that would affect the flux as well.